Good evening, everyone. Welcome to NPTEL tutorial session for the course Classics in Total Synthesis, taken by Professor Krishna P. Kaliappan. I am Sri Lakshmi S., a fifth year research scholar in IIT Bombay in the Department of Chemistry under Professor Krishna P. Kaliappan. So, I'll share the slide and we will wait for a couple of minutes to see anyone else is joining, or otherwise, we will start. 2 more minutes, we will wait and we will start this tutorial session. Okay, so for the last two tutorial sessions, we have seen the week 1 and week 2 lecture contents. We had a discussion on both those week lecture contents and we discussed many questions related to those topics discussed in the lectures, and we have solved week 0 assignment as well as week 1 assignment. So, as previous, we will discuss the week 3 lectures today in the first session of the tutorial, and then towards then we will be discussing some problems, and then we will discuss the week 2 assignment as well. So, this was the last problem which we discussed in the last session. Okay, so the discussion on lecture 11. Lecture 11 was basically about prostaglandins. So we have seen the Stokes total synthesis as well as Johnson's total synthesis of prostaglandin in this lecture. So Stokes total synthesis was for PGF2 alpha, and it involved the key chemical transformations of radical cyclization, which was followed by radical trapping and the application of a triply convergent approach for the total synthesis of minus PGE2, then plus or minus PGE2, and yeah, by Johnson. That was the lecture contents of this lecture 11. And in the Stokes total synthesis, the key reactions were a radical cyclization, which where he utilized a 5-exo radical cyclization and the radical trapping of that radical by another acceptor. Then we have also seen an intramolecular thermal rearrangement, which is known as Brook rearrangement. Um, I will come into that. What is Brook rearrangement? And in Stokes total synthesis, we have seen that he have completed that total synthesis in 7 steps from this cyclopentadiene. So now coming to this Brook rearrangement. So Brook rearrangement is the rearrangement of silicon groups from carbon to oxygen. That is, it is kind of migration, we can say migration of silicon from carbon to oxygen. So an important driving force for this shift is the bond strength of the silicon oxygen bond is much larger than the silicon carbon bond. That's why the silicon is migrating from carbon to oxygen. So this is the kind of rearrangement. So this is the compound. Here we have this silicon carbon bond, and when we are treating it with a base, this base will take this alcoholic proton to form this O minus, and then this O minus will attack upon this silicon and this bond will shift to this carbon. So it will form this kind of intermediate and finally resulting in this compound with where this carbon is having a negative charge, which will take a proton from the base and it will give this migrated product. Now we can see in the starting material it was carbon silicon bond, and in the product it is oxygen silicon bond. So that is a migration of silicon from carbon to oxygen is known as Brook rearrangement. And towards the next session of the prostaglandins, we have seen Johnson's total synthesis, where we have seen a triply convergent approach. And the key reaction was a one for addition to cyclopentanone followed by quenching the enolate with electrified. And here also the starting material was cyclopentadiene, and the one key reaction which other key reaction which was utilized was this MOFAT oxidation, and this total synthesis was completed in almost um, four longest linear steps with 32 percentage and 40 percentage overall. Yeah. So now we will see what is MOFAT oxidation. So MOFAT oxidation is a chemical reaction which will convert, as we can see here, this primary alcohol is converted into a corresponding aldehyde or ketone, and it uses DMSO and this dicyclohexyl carbodiamide as the reagents along with the proton source under mildly and neutral conditions. So that is basically an oxidation reaction. We can say it is a kind of modification of this one oxidation, and we will see what is the mechanism. So this compound, which is written as here, so that upon protonation will give this intermediate. Now what will happen from this DMSO, this O minus will attack at this carbon, and this positive charge on this nitrogen will be neutralized to form this particular intermediate. And then what happens is that our alcohol, that oxygen lone pairs will attack on the sulfur, leaving this proton to give this intermediate. Then what is happening? Again, one another nitrogen is there in this part, so that will take the proton from the one of the methyl group of DMSO, and this oxygen sulfur bond will break, and this group will leave to form this particular intermediate. Then again, the CH2 minus will take proton from this um, carbon which is attached to this oxygen, and that group will leave to form this ketone. So here DMSO we are using, and byproduct we are getting is DMS, and here we are using this particular compound which is converting into this byproduct. So that is a mechanism of MOFAT oxidation. I will give you 2 minutes for just going through this mechanism quickly. Okay, now moving to the lecture 12 contents, which was about the total synthesis of biotin and lactacystin. So there we have seen the application of intramolecular nitrine olefin cycloaddition reaction in the total synthesis of biotin. and application of stereoselective aldol reaction in the total synthesis of plus lactacystin by Baldwin and aldol coupling reaction in the total synthesis by Corey. So, biotin, as we know, is an essential vitamin for gluconeogenesis and fatty acid biosynthesis. It is having, as evident from this structure, it is having three stereocenters, 1, 2, and 3, and a tetrahydrothiophene ring, and a 5 carbon atom with a carboxylic group, carboxylic acid group. 5 carbon chain also it is having with a carboxylic group. Now, the first synthesis of this biotin was reported in 1982 by Hoffman La Roche, which was an enantiomer specific total synthesis, and where they used starting material as L-cysteine amino acid, and the key reaction was an intramolecular 3 plus 2 a reaction between cycloaddition reaction between nitron and alkene. So then we have seen a detailed explanation on what is 3 plus 2 deals a cycloaddition reaction or 1,3 dipolar cycloaddition reaction, where the nitron is having an electron deficient end and an electron rich end. So that will undergo a cycloaddition reaction with this uh, alkene to give a 5-membered ring. So a secondary orbital interaction is very small in the case of 3 plus 2 cycloaddition reaction. That's why most of the case endo-exo, that ratio will be controlled by the substrate or catalyst, and mostly exo will be favored because as we know exo is a sterically less hindered product. And the biotin total synthesis was completed in 11 linear steps and 8.19 percentage overall yield. Now coming to lactacystin, it is isolated from this Streptomyces species in 1991, and it is having two amino acids as we can see here, here one and here one, two amino acids and two N, that is N-acetyl cysteine, and the serine and cysteine it is having. The first total synthesis was reported by Corey in 1992, and here also the key steps involves aldol coupling, protection, and group selectivity. So it took 14 steps from 6 oxazolidine derivative from benzyl serine methyl ester with an overall yield of 6.04 percentage. Now coming to Baldwin's total synthesis, it was published in 1994 from the starting material R glutamate, and the key reaction was a stereoselective aldol reaction of a siloxypyrrole with aldehyde, thereby getting a quaternary center and the secondary alcohol in the correct stereo chemical form. And Baldwin took 20 steps with 4.27 percentage of overall yield. And one of the named reaction which we saw in this total synthesis was pinic oxidation. So this pinic oxidation is basically used for the conversion of an aldehyde into carboxylic acid. Usually, in most of the cases, when we are oxidizing an alcohol, sometimes we would end up with aldehyde instead of carboxylic acid. So that time, what we will do, we will isolate that aldehyde, and again we will subject it for pinic oxidation condition to get the carboxylic acid. So as we can see here, so here we are using this NaClO2 and NaH2PO4 in tertiary butanol water condition, and this alkene also we are using to get this carboxylic acid. Now we will see the mechanism and what is the role of each of this reagent in this mechanism. So here what is happening is that these two compounds, that is this ClO2 minus and this H2PO4 minus, will react and it will form this chlorous acid, that is Cl double bond OH. Now this oxygen lone pair of this aldehyde will take the proton from this chlorous acid, it will get protonated and form this species, protonated species. Now whatever that remaining O minus species is there in chlorous acid will attack at this carbonyl carbon center, and this positive charge on this oxygen will be neutralized. So that will be forming this kind of intermediate. Then what is happening, this hypochlorous acid, that is this OCl O, and it will take this proton and it will leave as this hypochlorous acid. What is remaining is R C double bond O, this double bond O and OH. So that will be the carboxylic acid. Now what will happen if we are not using this alkene is that this hypochlorous acid will again undergo a fragmentation type of reaction to form ClO2, Cl minus, OH minus. So if this is forming, this chlorous acid cannot be formed because this is ClO2 minus and here ClO2 is a neutral molecule. So if this side reaction is happening, this formation of this chlorous acid will not happen and the reaction cannot proceed further. So for that we are adding this alkene. So any alkene is okay. So what will happen is, instead of for performing this side reaction, whatever hypochlorous acid is forming, that will react with the alkene we are using and it will undergo this type of addition to form this byproduct. So two byproducts which we would be getting was hypochlorous acid, which can undergo the side reaction and suppress the reaction rate of the spinic oxidation. But if we are using an alkene for scavenging the side reaction, it will scavenge this hypochlorous acid to form this kind of intermediate and thereby promoting the reaction rate as well. So thereby we can get this aldehyde converted into carboxylic acid. Okay. Now the lecture 13 was about triquinanes, where we have seen the total synthesis of isocommine by Perrins and Fitger group, and we have also seen the application of intramolecular 2 plus 2 cycloaddition reaction in the total synthesis of isocommine by Perrin and acid catalyzed cascade rearrangement in the total synthesis of Fitzer. So, quinanes are the compounds having one 5-membered ring, as shown here. This we can call as a quinane. If there are two 5-membered ring, we will call it as diquinane. If there are three 5-membered ring, we will call it triquinane. So, triquinane can be linear, angular, propylene, or triquinacane, we can say. So, linear triquinanes can be cis anti cis or cis syn cis. Then different natural products like histidine, serapicol, coriolin, capnylane are having this linear type of triquinanes. And this angular triquinane is present in this isocamine, then sulfinane, pentalanine, and sulfiferolane. So there are two types of isocamine, alpha isocamine and beta isocamine. So which is depending on the position of the double bond. If it is internal double bond, we call it alpha isocamine, and if it is external double bond, we will call it beta isocamine. So there are two angular methyl groups which is a part of three contiguous quaternary carbon centers. Here also one methyl group, here also one methyl group, that are angular methyl group. So the Perung's total synthesis involved 2 plus 2 photocycloaddition and ring expansion by acid catalysis. and it has also utilized a Wagner-Mervin type rearrangement for the conversion of four-membered ring to five-membered ring. The starting material used was 2-methyl 1,3-cyclohexadione, and the total synthesis was completed in 42 percentage of overall yield in 6 longest linear steps in 1979. Now, in Fitcher's total synthesis, there was also this utilization of this Wagner-Medvin type rearrangement, and the starting material was acetone. The key reaction was, as we said earlier, the 2 plus 2 photocycle addition and acid catalyzed Wagner-Mervin type rearrangement. And it took 9 longest linear steps and 6.6 percentage of overall yield, and the synthesis was completed in the year 1988. So this is the mechanism of Wagner-Mervin rearrangement. As we can see here, this compound is having this Y group and this X group. So first, in the first step, this X group will eliminate or it will leave and it will form the secondary carbocation. Then this Y group will migrate from this position to this position so that a more stable tertiary carbocation is formed. Then if it is quenched by a nucleophile, it can form this compound, or if it is proton loss is happening, then it can form this alkane. An example is shown here. So in the presence of water, this can get protonated and water elimination will take place to form a carbocation over the center. Then this group can migrate to this position and it will form a more stable tertiary carbocation, more stable tertiary carbocation, which upon elimination will give this elimination loss of one proton will give this alkene. So this is a mechanism of Wagner-Mervin rearrangement. Now, the another key reaction which we discussed about tricunanes was ring expansion. So this is one of the example for ring expansion reaction. So what is happening? This double bond is get protonated in the presence of any acid. So it will give this carbocation. Then this ring will migrate to here, forming this carbocation which is quenched by a nucleophile to get this cyclopentane derivative. So we started with the cyclobutane derivative and we got the cyclopentane derivative. Here also, as we can see, this water OH molecule is getting protonated and it will eliminate as water molecule to form a carbocation. One of this group will migrate to this carbon to form a more stable carbocation, and as we said, if it is quenched by a nucleophile, it will form this compound. Or if it is undergoing an elimination reaction, that is proton loss is happening, then it can form this kind of compound. And here one rearrangement is also happening, that is this CH3 is migrating from this carbon to this carbon, and this carbocation is forming, and then elimination of one proton is happening to form this um, alkene derivative. Now, the next lecture of triquinanes was the synthesis of this alpha beta isocomanes and sulfipherferol 1651 by Ravel's group, where we have seen the application of Paterno-Bucci reaction. So, this isocomane was synthesized by Ravel and co-workers in 1994. They synthesized both alpha and beta isocomanes, and the key reaction was the fragmentation of a bridge system using cyclopentadiene as the starting material. Then we have also seen the Paterno-Bucci reaction, which is the 2 plus 2 photochemical reaction between alkene and a ketone to form an oxetane. Then we have seen the conversion of ester to ketone by beta ketosulfides, which are valuable synthetic intermediates which permit simple, economic, and efficient synthesis of ketones. Then we have seen the ring opening of oxetane, and this total synthesis was completed in 14 linear steps in 20 percentage of overall yield. And the total synthesis of sulfipherferol 6 in 5 on, which is another angular triquinane, was completed by Ravel's group in 1980. And the key reactions are same, which we told earlier. Paterno-Pucci reaction, conversion of ester to ketone, ring opening of oxetane, and the starting material they used was 2,4-dimethyl cyclopentadiene. And this was achieved in 5 steps with 35 percentage of overall yield. Then, in the last lecture, we have seen the total synthesis of triquinanes by radical cyclization, that is hierostine and capnellane. So, there we have seen the application of tandem radical cyclization, where these radicals can be generated by alkyl halides using AIBN and tributyl tin hydride. So, nitrogen is a good living group, so easy extrusion of this compound will generate the radical. And tetrabutyl tertiary tributyl tin hydride is used for the removal of nitro groups, radical cyclization. And then we have seen about Baldwin's rule as well. So exo endo, what is exo endo? When we call dig trig tet based on the carbon which is participating is sp2 or sp3. If the final radical is outside the ring, we will call it exo, and if the final radical is inside the ring, we will call it endo. The first authentic polyquinane natural product was historic acid C, which was isolated in 1966. And this linear triquinanes are four different types according to the position of the methyl group, which is two are shown here, hierostane and capnellane. We can see the difference between these two, the position of the angular methyl group. And the Curant's total synthesis of endohierostine utilize the key reactions Claisen rearrangement and tandem radical cyclization reaction. And the starting material used was 2-methyl cyclopentanone to get the core lactone. And this was completed in 1985 in 14 steps with 7.9 percentage of overall yield. And the capnellane total synthesis was done by Curant's group using a similar strategy, and using cyclopentanone as the starting material, and it was completed in 14 steps in 8 percentage of overall yield. So this is the Claisen rearrangement which we have seen in this total synthesis of triquinanes, hierustine and capnylane. So what is happening is that this is a aliphatic 3,3 sigma tropic rearrangement. So we can number it like 1, 2, 3, and this will be 1, 2, 3. So this 1 1 bond will break and this 3 3 bond is forming. So what is happening? This will shift over here. This double bond will shift over here, and this is shifting over here to form this compound. So it is expressed, it is shown in chair form like this. Then in the case of aromatic, same here, 1, 2, 3, and this is 1, 2, 3. So this group is actually migrating to here, and then again tautomerization will give this product. So that is aromatic Claisen rearrangement. It is basically a 3 3 sigma tropic rearrangement. So now we will start the discussion of some questions related to these topics which we saw here. So this is the first question. So the cyclopentadiene and this alpha beta unsaturated ketone, upon heating we will get this compound X, which on exposure to this photochemical condition we will get a compound Y. So which are these compounds X and Y out of these four options given here? So here, as we can see, this is an example for 4 plus 2 cycloaddition reaction between the cyclopentene and this one. So this is the diene and this will act as the dienophile to give this product which is N2 one as the major product. And here again when we are exposing this to photochemical condition, it can undergo this 2 plus 2 cycloaddition between this alkene and this ketone. So that Pattano-Bucci reaction will take place and it will form this compound. So the correct answer will be option C. Now moving to the next question. The major product of the following reaction. So here this compound upon protonation which compound can form. So we already told about ring expansion reaction. So you can think in that way. So here what is happening is that, so as I said earlier, protonation of this ketone will take place and then ring expansion to neutralize this positive charge on oxygen to form this intermediate. Then again this oxygen lone pair will come back and this will go here to take place a ring contraction. So this kind of a spiro system will form, and the correct answer will be option 4. Now, moving on to the next question. The major product formed in the following reaction. So, this diketene compound upon treatment with this trifluoroacetic acid, which can be the major product out of this four options given here. Okay, so here what is happening? First, in the starting material, the carbene generation will take place in the presence of this trifluoroacetic acid. So that will generate this carbene, and then this O-methoxy lone pair can fall here. This will come here, and this will attack over this carbene to form this intermediate. Then again, this negative charge will come here, and this will be O minus. Again, when this O minus will come back, this will come here, and this will get hydrolyzed to form this compound. So the correct answer would be option 3. This is a reaction which is mediated by carbene. So the next question is the major product formed in the following reaction. So this particular compound we are treating with the sodium methoxide, so which can form. So this is a keto group here, and other three options are also there. So which will be the major product? So here what is happening, this NaOMe will take the proton from here and that will attack over this position. This double bond will shift to here and this bromide will eliminate, which will result in this compound. Then again this NaOMe, this oxide will attack over this center and this bond will open to form this compound. So this is an example for Favorsky type of rearrangement. Now, the next question. The given reaction proceeds via. So, here, this two compounds we are treating with heating condition. This is forming. So, which is the reaction happening here? A 1,3 hydrogen shift followed by 4 plus 2 cycloaddition, 1,5 hydrogen shift followed by 4 plus 2 cycloaddition, 3 plus 2 cycloaddition followed by hydride shift, 4 plus 2 cycloaddition followed by alkyl shift. So here what is happening? First a 1,5 hydrogen shift is happening. So if we are considering this as 1, this will be 1, 2, 3, 4, and 5. So hydride is shifting from this position to this position to form this diene. Then a 4 plus 2 cycloaddition is happening, that is Diels-Alder reaction will happen to form this compound. So the correct answer is 1,5 hydrogen shift followed by 4 plus 2 cycloaddition. Okay, so this is the next question. This silyl compound, upon treatment with the cyclopentadiene in the presence of zinc chloride, which will be the major product here. So here what is happening? First, this zinc chloride will coordinate with this oxygen, and then this bond will break and the CF3 will eliminate, and this ZNO will also eliminate. So this bond is breaking, and this whole group will eliminate to form this carbocation. And then what is happening is this carbocation will undergo 1,3 dipolar cycloaddition. So this is the dipole and this is the dipolar of file, and it will undergo a 1,3 dipolar cycloaddition with the cyclopentadiene to form this compound, which this elimination of this SiMe3 will result in this dialkene compound. So that is the correct answer, option 4. So this is the example for 3 plus 2 cycloaddition reaction. The next question is, with respect to the following biogenetic conversion of chorismic acid A to 4-hydroxyphenyl pyruvic acid. So the structure is given here. This is chorismic acid and this is 4-hydroxyphenyl pyruvic acid. Out of the four statements given here, which statement is the correct one? So you have to identify which is X reaction X and which is this second reaction. Okay, so here the correct answer is first step which we discussed is a Claisen rearrangement. So here the numbering is also given. This is 1, 2, 3, and this is 1, 2, 3. So this bond is breaking and this bond is forming to get this compound. So the first is Claisen rearrangement. Then an oxidation is happening to convert this system into this quinone system. So here is one OH is missing, so that oxidation will undergo to get this quinone system. Then a decarboxylation is taking place for the elimination of this carboxylic acid to form this keto form, which can be written in this uh, enol form as well. So in the enol form, it is mistake here, it will be in the aromatic form. So the correct answer is option A is X is Claisen rearrangement and Y is oxidative decarboxylation. The next question: the following conversion involves, so this nitro compound upon treatment with this triethylamine and this alkyne, which will, this is the product, so which reaction is going on here? So first option is a dipole 1,3 dipolar species as reactive intermediate and a cycloaddition. Second option is a carbenium ion as reactive intermediate and a cycloaddition. Third option is a 1,3 dipolar species as reactive intermediate and an azavitic reaction. Fourth option, a carbanion as reactive intermediate and an azacope rearrangement. So here what is happening is that first, in the presence of triethylamine, the proton abstraction will take place from this carbon to form this anode. So this is now like a 1,3 dipolar dipole, so it can undergo 1,3 dipolar cycloaddition with this alkyne and it will form this 5 membered ring. Then again what is happening is that proton abstraction will take place from this position and that negative charge will fall off here. This will come here and the Cl will leave to form this compound. Then what will happen, this nitrogen lone pair will be nitrogen, negative charge on nitrogen will be quenched and we will be getting this compound. So here this 1,3 dipolar species is the reactive intermediate and a cycloaddition reaction is happening. So the correct answer is option 1. Now, the next question, the structure of A in the following reaction. So, this A is subjected for three consecutive reaction. First, photochemical condition and then ozonolysis and this treating with the sodium ethoxide in ethanol. We are getting this product. So, just you have to identify which is the starting material for this reaction to get this product. So here what is happening, so this can be rewritten in this form. So upon this photochemical condition exposure, this 2 plus 2 cycloaddition will happen to form this 4 membered ring. Then ozonolysis will help in the cleavage of this bond to get this ketoaldehyde, and then an aldol condensation will happen to form this compound. So first step is 2 plus 2 cycloaddition, then ozonolysis and aldol condensation. So the correct starting material is this one. The next question, the major product formed in the following reaction is, so this compound upon treatment with this magnesium in the first step, then carbon dioxide and hydrolysis, and then in the second step is oxyl chloride, and in the third step is triethylamine, which will be the product which we will be getting if we are treating this compound under these all conditions. So here what is happening is that, so under this magnesium condition this will form this Grignard reagent, and in the presence of carbon dioxide it will attack over this center to form this carboxylic acid. Then in the presence of this oxalyl chloride, a 2 plus 2 cycloaddition kind of reaction, um, no, in the presence of oxalyl chloride what is happening is that, mm, okay, so first this Grignard formation, then in the presence of carbon dioxide, this carboxylic acid will be forming. Then what will happen in the presence of oxyl chloride, this carboxylic acid will be converted into corresponding acid chloride. Then triethylamine will take this proton to form this ketene type of compound, and that will undergo 2 plus 2 cycloaddition with this double bond to form this compound. So the correct answer would be, here this double bond is there, and this 2 plus 2 should be at this position, and this also should not be there. There are some mistakes in this chem draw. So correct answer would be option 4. So first step, what is happening in the presence of magnesium, it will form the Grignard. Then carbon dioxide will make it carboxylic acid. Oxyl chloride will convert the carboxylic acid into carboxylic like acid chloride. Then triethylamine will make it into ketene, and then that will undergo 2 plus 2 cycloaddition with this double bond. So that's about the question discussion regarding the contents which we discussed. So we have now week 2 assignment also to discuss. I think maybe we can discuss it in the next tutorial session. So today we have seen the week 3 lecture contents, and as well as today we have seen this week 3 lecture content. and some questions related to that and the mechanisms. And the mechanisms related to the reactions which we saw in the week 3 lecture contents. I hope all this question discussions session is clear. I hope there is no doubts regarding any questions which we discussed, and if there is any doubt regarding any of the content of the lecture or the questions which we discuss, you can talk to me anytime. You can ask in the next tutorial session as well. Please go through whatever we have discussed, all the questions and answers as well. So in the next week we will start with this week 2 assignment, then we will three the week 4 lecture contents and the remaining questions as well. So I hope this session was useful, and thank you for joining. Thank you.